Hello everyone. Today we are going to outline the location of roots of the polynomial of the shown form. So here we have coefficients as cn minus 1, cn minus 2, all the way to c0. And we have the condition that absolute values of these coefficients equal 1. In other words, it can be plus or minus 1. So they are all real. So it can either be plus 1 or minus 1. Of course, determining their roots is not an easy job. But we are going to bound and outline and draw some beautiful graphs today. So let's get into some theory before we plot. So this is the polynomial that we are analyzing right now. F of x equal to x bar n plus cn minus 1 x bar n minus 1 plus cn minus 2 x bar n minus 2 all the way till c1x plus c0, but with the conditions that all the ci are real and mod of ci equals 1. So in other words, ci belong to 1 minus 1. The set containing 1 minus 1, or ci is plus or minus 1. So this is an equivalent condition. And we are now about to describe the location of the roots so that we can approximately determine the characteristics of this polynomial. Have in mind that determining the position and the location of the roots can provide with us a lot of properties of those polynomials. So first, let me substitute a root, a possible real root. So let alpha be a real root of f of x. And we are going to find how this root shall behave. Later on, we can also extend it to complex numbers. But first, let's stick to real numbers. So, substituting it, we get alpha power n plus cn minus 1 alpha power n minus 1 plus cn minus 2 alpha power n minus 2 all the way till c1 alpha plus c0 equals 0. So let's move the alpha power n to the RHS. So this is equal to alpha power n and with the negative sign. Now take modulus both sides and you get the following. If you take modulus, the negative sign in the RHS can be removed. And now we know that mod of alpha power n is mod alpha power n by the properties of modulus. We know that modulus can be separated with multiplication and can be considered individually. So we have the LHS as it is, and let's apply it to some inequality that we are already aware of. We are aware of mod x plus mod y is greater than or equal to mod of x plus y. This is true even if x and y are complex numbers. And applying this for n numbers, let's see what can be attained. So consider the modulus individually. So mod of cn minus 1 alpha power n minus 1 plus mod of cn minus 2 alpha power n minus 2 till mod of c1 alpha plus mod of c0 is greater than or equal to the actual LHS of the equation that we arrived at. N minus 2 till c1 alpha plus c0. But we know that it is equal to mod alpha power m. So let's have that in mind. Now, notice that the absolute value of all the CIs equal 1. And for example, mod of Ci power alpha I equals mod Ci into mod alpha power I. And mod Ci equals 1, mod alpha power I become mod alpha whole power I due to the same property of modulus. And now just replace it with mod alpha power n minus 1 plus mod alpha power n minus 2, so on till mod alpha plus 1 being greater than or equal to mod alpha power n. All right. So let mod alpha be equal to t. So clearly t belongs to positive real numbers. So substituting it, we get t power n minus 1 plus t power n minus 2, so on till t plus 1 is greater than or equal to t power n. But LHS is nothing but a GP, and we can simplify it using the common ratio t and initial term as 1. So doing which we get t power n, because there are n terms, minus 1 by t minus 1 is greater than or equal to t power n. But here we can conclude something. So now this inequality will not be true for t greater than or equal to 2. Let's see why. Suppose if you consider this, then t power n minus 1 is clearly less than t power n. And when you divide it by t minus 1, which is some number greater than 1 or equal to 1, then you will still further decrease this. You will still further decrease the value of t power n minus 1 by dividing it with t minus 1 for t greater than or equal to 2. Now this means that the inequality can't hold true. And hence, one can conclude that mod alpha must be strictly less than 2. So this is a conclusion that can be reached. So in other words, alpha can be less than 2 and greater than minus 2. But we do not know whether there exists a real root. So this is just under the assumption that if it exists, then it must be between minus 2 to 2. So again, delineating the location of roots shall give you a lot of characteristics of the polynomial. So this is the condition for real numbers, which is a root of this polynomial. But this can also be extended to complex number, because we know that this inequality is still true for complex numbers, x and y in complex numbers. So thus, mod alpha less than 2 should imply that absolute value of any complex root should be less than 2. Or if you go into the complex plane to locate the roots, then it must be in the circle of radius 2 centered at origin. But we can't plot the graph of polynomials in 3D easily. But let's try out for two-dimensional plot that can sketch the roots which are real. And you will observe that it's between minus 2 and 2. So here is the polynomial 1 minus x square minus x cube plus x power 4 plus x power 5. And we are using Desmos, which is a graphing calculator online for free. You may also try to plot this yourself. And the plot of which is available in the right side And you can see that the roots are between -2 to 2. So this is evident for this polynomial. And even if you alternate the signs, as I am trying to do here, you could see that the roots do not transcend the boundary of -2 and +2. So for example, if it's minus x power 4, it does not do. Let's say -2 plus x cube. As you could see, it's getting closer to -2, but it will never touch it. So there are a lot of parameters over here that for some coefficient it might go close to -2 and for some it might not. But the bound is really important here. So of course, after a while, when it reaches the graph to sufficient height, it will extend beyond -2. But as you could see, for the discussion on roots of the polynomial, it shall never cross the boundary. So you can change this a lot. Also, you can add multiple coefficients to it to see the same characteristic. So you can also plot this by yourself and have fun with plotting them in Desmos. So let's meet in the next video. Happy learning. Bye.